तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Last couple of lectures we were discussing about the physicochemical processes for water and wastewater treatment. We have seen the plain sedimentation, coagulation, flocculation, softening, filtration and disinfection for the treatment of water and wastewater. And we have also seen that the physicochemical processes, whatever we were discussing, it is mainly used for water treatment. Okay. Why we are using those processes for water treatment? It is all depending upon the nature of the pollutant present in the water. In the nature of pollutant, whatever is present in the raw water, whatever we are collecting from surface sources or groundwater sources is entirely different from the water, whatever is coming after the use by the people or whatever is coming through the sewers. Okay. The waste, or we call them as wastewater. Wastewater, the quality of solids or quality of water or quality of pollutants present is entirely different. So, depending upon the pollution nature, we have to select suitable processes. So, today we will be discussing about biological processes. These biological processes are mainly used for wastewater treatment. The reason is the solids present in wastewater is mostly organic in nature. So, this organic matter can be removed easily by biological means or by the action of microorganisms, because microorganisms can use them as their food and convert them into carbon dioxide and water if it is in aerobic condition, or they can convert it into carbon dioxide and methane if it is in anaerobic condition, or inorganic substances like nitrate or nitrogen gas, depending upon the process how we are designing. So, the biological process, the process is based upon the nature of the solids, but most of the time this biological process are being used for wastewater treatment. So, now we will see what is this biological processes, what are the different processes or operations involved in biological treatment. So, biological treatment also have unit operations and unit processes, because the wastewater, you know, it will be containing a series of or different types of solids present in that one. So, different solids we can remove by different methods. So, unit operations are also essential for wastewater treatment, and we have already discussed what is a unit operation. Unit operation is the one in which the contaminant removal is by physical forces. Most of the time it will be by gravity settling or by flotation, because if the density is higher, the gravity force will be predominant and it will be settling down, and if the density is less compared to the liquid in which the solids are present, then what will happen? The pollutant or the solids will be floating. So, these are the two main mechanisms being used in unit operations. Then coming to unit processes, we have seen that unit processes are the ones in which we use either biological or chemical reactions or both together. So, biological process also involves biological reactions, because it is not merely because of the physical forces the removal of solids are taking place. And whenever we talk about biological processes, we talk about a reactor. Means most of the processes are taking place in a closed container. So, that is why we are referring it as a reactor. Reactor is nothing but a vessel or containment structure along with all of its appurtenances. So, the vessel in which the reaction is taking place, that is known as a reactor, because any process, especially the biological process, whenever we term or we call it as a reactor. So, whatever I have already mentioned, wastewater treatment system is a combination of unit operations and unit processes, and the selection of the treatment is depending upon the quality of the pollutant present in that one, or there is no distinction or difference between water treatment and wastewater treatment. Okay. If the nature of the pollutant are same in water and wastewater, then we can go for the same type of treatment, or if the nature of the pollutant and are different, then we have to adopt different processes. It is all based upon the nature of the pollutant. That is the most important point we have to be clear about. Now we will see, coming to the wastewater treatment. So how the treatment system is? It can be divided into 3 different groups. One is primary treatment, second one is secondary treatment, and the third one is tertiary treatment. Primary treatment basically consists of a series of unit operations. That means the treatment units all are working based upon physical forces. So the major objective of this one or this primary treatment is to remove the suspended solids from the system, because the wastewater also will be having lot of suspended solids. So if we can remove them by either gravity or by flotation, then it will be very good, because the load coming to the next treatment system will be very less. Because if you see the solids in wastewater treatment, we can see that there will be lot of suspended solids, floating material, and colloidal solids, and even dissolved solids. When we talk about the solids, the removal of dissolved and colloidal solids are much difficult, because gravity force or flotation may not be effective for the removal of that one. So in primary treatment, basically what we are doing is removal of the solids which is easily separable. And coming to the secondary treatment, in wastewater mostly we go for biological treatment, because the most of the solids present in the wastewater is organic in nature. So we can easily use the microorganism for the removal of them. So here in secondary treatment, it is biological conversion of dissolved and colloidal organics. So that is what is happening in secondary treatment. Now coming to the tertiary treatment, what happens? Most of the organic matter will be removed in the secondary treatment, but there will be some other solids left over which cannot be removed biologically. So if you want to remove that one to meet the effluent discharge standard, then we have to go for some other treatment which is able to remove those solids. For example, if you talk about wastewater, it will be containing lot of ammonia, nitrogen, phosphorus, etc., or in other words, lot of nutrients present in the system. So nutrient removal can be achieved by biological process, and sometimes we can even go for physico-chemical processes or adsorption, ion exchange, etc., for the removal of nutrients. And if we talk about the wastewater coming from industries, it will be having so many other toxic compounds. Most of them are synabiotic in nature. For example, if heavy metals are removed, heavy metals are present in the wastewater. If we go for biological treatment, most of the microorganisms will not be able to survive under high concentration of heavy metals, because heavy metals itself is very toxic, and it will be getting accumulated on the microbial cells, and gradually what will happen, the efficiency of the microbial system will be decreasing, and it will be retarding the efficiency of your secondary treatment also. So usually what we do is, to remove such toxic compounds, we go for tertiary treatment. After the tertiary treatment, you will be getting of water which can be reused for our common purpose like gardening, and if we can give the treatment up to the extent possible to meet drinking water standards, then we can even use the water for drinking water purpose, because nowadays the water sources are diminishing. So the recycle and reuse concept is coming up. So the tertiary treatment is also becoming very important nowadays. Now we will see what is a typical primary treatment system. So here we can see the raw water is coming, and this is the screen. The major purpose of the screen is to remove the floating material. So, and we have already seen in detail how to design a screen, and also I am not going into details. And from the screens we will be getting big solids or the floating solids. So one commutator is here which will be shredding the floating material into small particles. Then after the screens, next come the grid channel or grid chamber. The major purpose of the grid chamber is to remove grid or sand and silt whatever is present in the wastewater, because if it goes to the secondary treatment system, okay, it will be reducing the effective volume of the treatment system because it will be getting accumulated there. So, before sending the wastewater to the secondary treatment, we have to remove the sand and silt particle or inorganic material from the water. Inorganic, which is easily settlable material, we have to remove. So, that is the purpose of this grid channel. So, when we design the grid channel, the most important point we have to consider is no organic material is getting settled here in the grid chamber, because if organic material get deposited there, what will happen? The anaerobic condition prevail and microorganisms are already present there. So, what will happen? Anaerobic degradation starts. So, the efficiency of the grid chamber will be reducing. Moreover, there will be lot of gas production and it will be creating odor problems and all. So, the grid chamber should be designed only for the removal of sand, silt and other dense inorganic material. Then after the grid chamber, we may go for an equalization chamber, because in the first lectures we were discussing about how the flow is fluctuating when we talk about wastewater, because the water usage pattern in the domestic area or in the industrial area or commercial area will be varying with respect to the time, because the morning time we will be having more water usage, then it will be peaking up towards the lunch time, then it will be decreasing, and when we come to the midnight time, okay, almost there will not be any wastewater production. So, if you want to have a equalization chamber, what will happen? The flow to your treatment systems will not be uniform, that will be affecting your treatment efficiency. So, we may have to go for a equalization chamber. So, when we design the equalization chamber, we have to see that, okay, no other biological reactions are taking place here. So, what we usually do is the solids will be settling down. So, you have to provide a shaker, or we have to mix the water properly, so that uniform water characteristics or the wastewater with uniform characteristics will be entering into the other treatment systems. So, this is the equalization chamber, and equalization chamber can be online and offline, because if most of the time the flow is uniform and sometimes the peak factor is coming. So, what we can do is, the whatever is the excess than the design flow, that can be collected in the offline equalization chamber, and the remaining flow will be going to the treatment system, and whenever the flow is lower than the design flow, then we can pump it from the equalization chamber. So, depending upon the nature of the flow, we have to design suitable equalization chamber. After the equalization chamber, next unit coming in primary treatment is primary clarifier or sedimentation tank. So, when we talk about wastewater, the solids present in the wastewater are not discrete in nature. So, we cannot use Stokes law, whatever we were discussing. So, these particulates are of this flocculant in nature, and in wastewater if you see, the concentration of the particulates are lower. So, this is coming under low concentration flocculant particle or type 2 settling. So, the primary clarifier, especially for domestic wastewater, we have to design based upon type 2 settling. And here again we have to be very careful. If we give high detention time, what will happen? The organic material will be settling down in the tank and the putrefaction will be taking place, because anaerobic condition will be prevailing and the wastewater will be having lot of anaerobic microorganisms. So, they will be start decaying the organic matter. As a result, the gas production will be there, especially carbon dioxide and methane, and moreover, if the wastewater is containing lot of sulphate, what will happen? Under anaerobic condition, this sulphate will be getting converted to hydrogen sulphate. So, along with the gases, hydrogen sulphate also will be coming up, and that will be creating odor problem. So, the detention time in primary clarifier of wastewater treatment system should be in the range of 1.5 to 2 hours. Though the design criteria is not detention time, we have to design it for surface overflow rate. We have to check the detention time, because the detention time, if it is high, your tank efficiency will be decreasing because of the gas formation, and if gas formation is there, lot of turbulence is there, that will be lifting all the settled particle and it will be acting as another biological reactor. So, you will not be achieving the very purpose of your clarifier here. So, that is very, very important. We have to design based upon surface overflow rate, but we have to see that the detention time whatever is coming here is within the permissible limit. Once the primary treatment is over, the wastewater is going to the secondary treatment. So, now we will see what are the secondary treatment systems usually we use in wastewater treatment. Okay. So, most commonly used treatment system in wastewater treatment, especially domestic wastewater treatment, is activated sludge process. Nowadays, anaerobic systems are becoming more and more popular, because if you talk about aerobic system, okay, we will see in detail afterwards, the power consumption will be very, very high. So, nowadays anaerobic processes are taking up more and more interest. Many treatment units are going for anaerobic units. So, in secondary, if it is an activated sludge process, what all are the components present? There is an aerator, then the aerator is there, okay, and the wastewater is aerated. So, what will happen? The organic matter present in the wastewater will be utilized by the microorganism and it will be converted to new cells and carbon dioxide and water. A portion will be going as carbon dioxide and water and remaining will be converted to biomass. So, in the aeration tank you will be getting more and more biomass, or in other words your solids in the form of the solids whichever is present in dissolved form will be getting converted to colloidal form. Okay. Now, we have to separate the solids, otherwise practically speaking there will not be any treatment taking place, because you are just converting the dissolved solids into colloidal form, or colloidal form is nothing but the microbial cells. So, how can we separate them? So, we have to have a clarifier. This is the secondary clarifier. So, how the clarification is taking place? These microorganisms are able to excrete some extracellular polymers. So, that extracellular polymers will be acting as coagulants and they will be flocculating the microbial cells. So, you will be getting bigger flocks. So, that flocks can be easily settled in this secondary clarifier. So, and secondary clarifier design we have to do based upon zone settling and sludge thickening principle, because here they are flocculant in nature and the concentration is medium in the initial stages. When we go to the bottom of the tank, the concentration will be very, very high. So, you will be having zone settling and compression settling. So, this design we will see in detail afterwards. And what will happen? Here the sludge is settling. So, a portion of the sludge is going back to the aerator, because we have to maintain a constant microbial concentration in the aeration tank, and remaining sludge will be going to sludge treatment, because we cannot just dispose this sludge off, because this sludge or the solids whatever we are getting in the secondary sedimentation tank is nothing but microorganisms, because if you discharge them to the nature, what will happen? The putrefaction will be starting. So, as a result what will happen? Bad smell or odor will be generated. So, we have to subject this sludge for further treatment, then only we can dispose that one. So, now after the secondary treatment, okay, this is here I was explaining about activated sludge process, but in wastewater treatment we can use many different types of treatments. So, this is another one. Here we are using an attached treatment system, that is trickling filter. So, whatever is the water coming after the primary treatment unit is entering into the attached growth filter. So, here the microorganisms are stationary. So, the wastewater is flowing or trickling through the filter. So, what will happen? The microorganism whatever is present there will be utilizing the organic matter. As a result, more and more cells will be generated and the thickness of the film in the filter will be going on increasing, and a portion will be getting converted into carbon dioxide and water. So, since the microorganisms are attached, you will be getting somewhat clarified effluent from the system. But one problem is there, as we have seen, the thickness of the microbial film, whatever is attached to the surface of the matrix, will be keep on increasing. So, after some time what will happen? The food will not be penetrating through the microbial film. So, the microorganism which is attached to the solid, which is sitting in the innermost of the film, they may not be getting the food. So, what will happen? The microorganism will be undergoing auto-oxidation. As a result, the microbial film may be sloughing off from the filter media. That is one reason. And another one is the water is flowing through the filter media. So, because of the shear stress created by the water, so if the thickness of the film is very high, it will be shearing off. So, some microorganism in the form of sloughed sludge will be coming. So, if you want to remove that one, here we have to provide a clarifier, and whatever the clarifier the effluent is coming, here we are recycling this one. So, this we have to be careful. In attached closed system, we are not recycling the sludge, we are recycling only the clarified water, but in activated sludge process, we are recycling a portion of the sludge. Okay, why we are doing so, we will see in detail in the coming lectures. And whatever is the sludge here, it is going to sludge treatment, because this sludge is also consists of active biomass. So, we cannot dispose it off just like that. So, we have to go for further treatment, sludge treatment. Most of the time we go for sludge digestion in anaerobic systems. And from here the effluent will be going for further treatment. Okay, if you want to reuse or recycle the water, or if it is not meeting the effluent standards. If it is meeting the effluent standards and we do not want to reuse the water, then we can let it to the stream. This flow diagram shows how can we treat the sludge. So, whatever the sludge generated either in the attached growth system or in suspended growth system, what we have to do first is thicken the sludge, because the sludge density will be in the order of 1.04 to 1.05, and it will be containing around 95 to 98% of water. So, the volume of the sludge will be very high. So, if the volume of the sludge is very high, so the handling problem will be too much. So, it is always advisable to have less volume of sludge. So, that is the purpose of this sludge thickener. So, get maximum concentration of the sludge in the thickener itself, and afterwards what will happen? From here it will be going to the first stage of digester, and again second stage of digester, and whatever is the water coming from the sludge thickener or the digesters, it will be going to the secondary treatment or primary treatment again it will be coming back to the system, and the sludge after the digester, it will be going to sludge disposal or sludge drying beds, and afterwards we can use this sludge as a manure. And when we use the sludge digesters, we will be getting lot of gases like methane, carbon dioxide, ammonia, etc. If lot of methane is there, we can use it as a fuel, otherwise we have to flare it up, because we are not supposed to release this methane to the atmosphere, because we all know that methane is a contributor of greenhouse gas, or methane is one of the greenhouse gases. So, what will happen if the concentration of methane in the atmosphere increases? The outgoing sun rays or radiation will be captured by or absorbed by these gases, then the global warming or the temperature of the earth will be increasing. That will be leading to global warming and all. So, methane is not allowed to send it to the atmosphere, we have to take care of that one. Now, we will see there are certain biological treatment processes which do not require a primary treatment as such, because whatever we have discussed so far, activated sludge process or trickling filters need primary treatment, because it will not be able to handle the suspended solids coming to the system. But certain treatment systems like oxidation pond and aerated lagoons, they do not require a particular primary treatment system or equalization system, because this itself will be acting as a primary treatment as well as a secondary treatment unit. So, raw water whatever is generated, it will be directly coming to the oxidation pond. This oxidation pond is very much similar to the natural processes. Here we are utilizing the symbiosis of algae and microorganism, especially bacteria, for the treatment of wastewater. So, here the raw wastewater, whatever the inorganic substances present there, it will be settling down, and floating material we can remove using a screen, and afterwards whatever is coming here, it will be getting converted into carbon dioxide and water. The detention time is so high, so the microbial population generated in the system will not be so high like activated sludge process, and whatever is coming out, this can be sent for further treatment or to the stream. But here if you see oxidation pond, lot of algae will be there, so your total COD whatever is coming out of the system will be always higher. But if you remove the algae, the soluble BOD will be within the permissible limit, but total BOD will be always higher. So, most of the time it may not be meeting the standards for discharging in the stream. So, we have to be careful about that one. And another one is aerated lagoon. Here also it is just like an oxidation pond. The only difference is here we have some mechanical aerators. In oxidation pond we do not have any mechanical aeration system. The oxygen transfer is taking place naturally, but to increase the efficiency here in aerated lagoon, what we do, we provide aerators, but we do not have to go for any primary treatment, and here after the treatment it goes to either for further treatment or to streams or land for the discharge. Okay. So, this is the basic units of a wastewater treatment system. That means primary treatment should be there, then secondary and tertiary based upon the quality of treated water we need or treated wastewater we need. Now, before going into the process, we will see the fundamentals of the process, because unless we know the fundamentals, it will be very difficult to design the reactor or the biological system. So, we have seen that the biological processes are taking place in reactors. Reactors are nothing but a closed container with all the control devices, and in biological process also it is a reaction, it is only biological reaction or biochemical reaction. Whatever we have discussed in physicochemical processes, we have seen various chemical reactions which is mediated by chemicals, but in biological processes the biochemical reactions are mediated by microorganisms and the enzymes whatever is present in the microorganism. So, whenever we talk about a reaction, either it is a chemical reaction or a biochemical reaction, okay, we can classify the reaction based upon stoichiometric basis and kinetic basis. But whenever we talk about biological process, okay, we usually classify the reaction based upon the kinetics, because the stoichiometry, most of the organic matter present in the wastewater are so complex. So, we won't be able to make the reaction comparison based upon stoichiometry. When we classify the reactions based upon the kinetic, so we can see different types of reactions, okay, how the rate of reactions are depending upon, or what is the matter which control the reaction rate, okay. Depending upon that one, we can classify the reactions into zero order, first order, second order or nth order reactions, or the rate of reaction or the classification of the reaction can be based upon the rate of reaction and concentration of the reactants, or we can write like this: rate of any reaction is equal to concentration raised to n, okay. So, depending upon the value of n, okay, we can classify the reaction as zero order, one order, first order, second order or nth order, or this equation we can change it to log rate is equal to n into log concentration. So, if you take both logarithm on both sides, we can write log rate equal to n into log concentration, or rate of change of concentration dC by dt is equal to C raised to n. This way we can write any reaction if we are classifying them based upon the kinetic basis. So, now we will see how can we determine the rate of any reaction. So, if we want to determine the rate of any reaction, we have to conduct laboratory experiments. Once you get the laboratory experiments results, what we have to do? We have to plot logarithm of the concentration, no, logarithm of the rate with respect to logarithm of the concentration. So whatever the slope we are getting, based upon that one we can find out whether the reaction is 0 order, first order or second order. So this is the example of a 0 order reaction. The rate and concentration are independent. See here we can see, and here the rate is linearly varying with the concentration. So this is first order. Okay, here the rate is varying. The slope, if you see take, it is 2:1. So the order of the reaction is second order. So the rate and concentration of reactants and product can be obtained by experiments. So once we have to conduct the experiments, and whatever the results we are getting, we have to plot log rate versus log concentration. Then we can find out what is the rate of the equation, because this is very important when we talk about the reactors, the reactor volume and the time required to achieve the desired treatment. We have to know what is the rate of the reaction. Now we will see 0 order, first order and second order reactions in detail. 0 order reaction, okay, if you want to, the reaction that produces at a rate independent of the concentration of reactants, that is 0 order reaction. Whatever be the concentration of the reactants, the rate will be independent of the reaction or reactant concentration, or the rate is independent of the reactant concentration, that is known as 0 order reaction. So for example, we have a reactant A and it is producing a product B. So we can write like this, minus dA by dt is equal to K into A raised to 0. That this minus sign is coming because you know that when a reactant is reacting and a product is formed, the reactant concentration or the mass of the reactant will be getting reduced with respect to time. So that is why whenever we write dA by dt, we use a negative sign. If the reactant concentration is increasing in the reversible direction, then we have to use a positive sign. So the rate of reaction is equal to K into A raised to 0, because it is independent of the mass of the reactant present here. So this term will become 1. So you will be getting minus dA by dt is equal to K, or rate of disappearance of minus dA by dt is nothing but rate of disappearance of A, and K is the reaction rate constant, or the rate of disappearance of A is a constant. That is what it means, or this is the 0 order reaction. Now we will see each term in detail. C represent the concentration of A at any time t. So if we know the concentration of C at any time, we can find out what is the rate of disappearance of A, and if you want to find out what is C at any time, we can integrate this expression, then we will be getting minus Kt plus concentration of integration, because minus dC by dt is equal to K. So minus dC is equal to K into dt. So if you integrate that one, we will be getting C is equal to minus Kt plus concentration of integration. And how can we find out the concentration of integration? So we can put this condition. What is the concentration when T is equal to 0? T is equal to 0, the concentration will be nothing but the initial concentration, C is equal to C naught, that is the concentration of pollutant or the reactant, whatever is coming to your system. So here C naught is the constant of integration, or we can write like this, C minus C naught is equal to minus Kt. Or if you plot the equation, so it will be coming like this. Initially it is starting from C naught and the concentration will be decreasing like this. The slope is minus K. Now we will see what is a first order reaction or 0 order reaction. We have seen that the rate of change of concentration is independent of the concentration of the reactant present. Okay, it will be decreasing at a constant rate. Now coming to first order reaction, same example we will take. A reactant A is there and it is reacting and giving a product P. So if you want to write the rate at which the concentration of A is changing, we can write like this, minus dC by dt, because A is disappearing as P is getting formed, and it is equal to K into C raised to plus 1. That means the rate of disappearance is proportional to the concentration of the reactants present, or we can write it write it as Kc. So here also we can find out, okay, what is the concentration at any time minus dc by c. This c, if we take this side, we will be getting k into dt, or ln c naught by c is equal to kt, because c naught here also we will be getting a constant of integration, and that is nothing but ln c naught. So we will be getting ln c naught by c is equal to kt, or if you take logarithm in both sides with 10 base, we will be getting c naught by c is equal to kt by 2.3. So if you plot log c versus time, then you will be getting the line like this with a slope of minus 0.434 k. Or in other ways, other words, the concentration or the rate of the reaction is directly proportional to the concentration of the reactant present in the system. And when we talk about the biological processes, we assume that almost all the reactions are first order, but we can see later up to certain level the reactions are first order, but if the concentration is very high, then the reaction will be of zero order. You have seen Monod's equation there, we have seen, isn't it, as the concentration of the substrate increase, afterwards the substrate will be becoming independent of the microbial or microbial concentration will become independent of the substrate concentration. So that is an example of zero order reaction. But if the substrate is limited and if you see the microbial concentration, what will happen? It is a first order reaction. Or other example of this first order reaction is whatever we have discussed last class. We have talked about the Chick's law of disinfection. There also we have seen that the rate of kill of microorganism is directly proportional to the number of microorganisms present initially. So that is also an example of first order reaction. Now we will see what is the second order reaction. Here also some reactant is there, the reactant is reacting and the product is formed. So if you want to find out what is the rate of change of concentration of A with respect to time, that is nothing but minus dc by dt, that is equal to k into c squared. So dou c by c squared is equal to k into dt, or we can see that 1 by c minus 1 by c naught is equal to k into c. Or if you plot 1 by c versus t, you will be getting a line like this. Okay, so this is an example of second order reaction. Okay, so now we have seen that how to find out the order of the reaction, whether it is zero order, first order, second order, or end order reaction. Okay, we can plot the log concentration and log rate, and whether we are getting a straight line, and depending upon the slope, we can find out which is the order of the reaction. So now we are clear, okay, how the reaction rate is changing. Now we have to discuss about what are the different reactors available, what are the different types of reactors available, because I have already mentioned that most of the biological treatment system, okay, will be, or most of the biological processes are taking place in a reactor. So we should know which type of a reactor is most effective, or how can we control the volume of the reactor without affecting the removal efficiency. So for that we should have a basic idea about what are the different types of reactors available. So basically we classify the reactors into three different categories. One is completely mixed batch reactor, another one is continuous flow stirred tank reactor, and third one is plug flow reactor. We will go little detail of each one, because this is very important. In which way we are designing our reactor system, the efficiency will be changing accordingly, and we will see how the time of reaction or time required for the wastewater to be there in the treatment system varies with respect to the configuration or the type of the reactor. So first we will talk about the completely mixed batch reactor, okay, or we call it as a CMBR, completely mixed batch reactor. So this CMBR is a closed system. That means we take the reactants, whatever we have to reduce or treat, in a closed container or in a reactor, and there will not be any inflow or any outflow from the system. That is what we call it as a closed system. Nothing is coming to the system or nothing is going out of the system. So, whatever is there in the system, it will be remaining there. That is what here. CMB is a closed system, no flow into the system, no flow out of the system. So, if you want to find out the rate of change of mass of A within the reactor, A is nothing but the reactants. So, how is the rate of mass of A changing within the reactor? That is nothing but the rate of creation of A within the reactor or rate of destruction of A within the reactor. Okay. Sometimes the product, we are interested in the product, then naturally it is a creation. So, sometimes we are interested in destructing the pollutant. So, then it will become destruction. So, how can we find out this one? So, we can write the equation like this. V is our reactor volume. So, V into dC by dt. This is nothing but the rate of change of mass or concentration of A within the system. That is the net change. That is equal to, that is nothing but V into dC by dt reaction, because we are not allowing anything to come into the system or go out of the system. So, because of that one, no mass is changing. So, whatever mass is changing within the reactor is because of reaction. So, that is why we can write it as what is the net change in concentration of C within the system is equal to V into dC by dt reaction. And we have already told that in most of the cases we are assuming that the biological reactions are of first order. So, if the reaction is first order, then we can replace this dC by dt as K into C, because first order the reaction rate is directly proportional to the concentration of the reactants. So, this will become dC by dt is equal to K into C. So, to find out what is the time required in the reactor or what is the time required for the desired reaction, we can find out like this. T is equal to, if you integrate this one, we will be getting, okay, dC by C is equal to KT or ln C naught by C is equal to KT. So, we can find out what is the time required. T is equal to nothing but 1 by K into ln C by CD. This CD is the concentration desired. Okay, after the treatment, what is the concentration we want, and C is the initial concentration. So, if we know these two concentration, we can find out what is the time required in the treatment unit. This time is the parameter which decides the volume of the reactor. So, this time is nothing but the hydraulic retention time. So, hydraulic retention time we can find out by dividing the volume with the Q. Q is the flow rate. So, if T is more, definitely our reactor volume will be very high. Now, we will talk about the continuous flow stirred tank reactor. This is the second type of reactor. This is not a closed system because there is an inflow and there is an outflow. So, whatever is the reactants there in the reactor, it will be continuously getting mixed. And we assume that the reactor is working under steady state condition. So, what is happening here? You see, this is Q is the flow rate. At a rate of Q, wastewater is coming to the system, and the concentration of the substance of interest or the concentration of the pollutant or the concentration of the reactant is C naught, and the volume of the reactor is V. So, as soon as this flow enters in the reactor, what is happening? There is a continuous mixing taking place in the reactor. So, because of the mixing, the concentration C naught will be getting changed to CE instantaneously. Okay, this CE is nothing but it is the concentration whatever is coming out. So, in a continuous flow stirred tank reactor, the concentration gradient is very less compared to a CMB reactor or completely mixed batch reactor. So, naturally, since most of the reactions the concentration gradient is the driving force, so the volume required in a continuously flow stirred tank reactor is more than a CMBR reactor. So, that is an important point. CSTR reactor needs more volume compared to CMBR reactor or plug flow reactor. The reason is here the concentration gradient available for the reaction is much less compared to the other reactor. So, now we will see how to find out the detention time or the HRT in a CSTR reactor if you are interested to get a desired amount of treatment efficiency. So at steady state we will take the mass balance. So here we can see the net rate of change of mass of A within the reactor, or net rate of change of concentration of A within the reactor, which is equal to, because it is an open system, so there is some inflow, there is some outflow, and there is some reaction. So the net rate of change of mass is equal to rate of increase in mass of A due to its presence in the influent, because Q into C naught is coming to the system always, and rate of decrease in mass of A due to removal in the effluent, and Q into C is going out of the system, so that is this one. This is incoming flow, this is outgoing flow. Because of that one, some mass is going out of the system. And now the rate of increase or decrease of A due to its process because of the reaction, that is the third term. One is because of the reaction, another one is because of the incoming flow, and another one is because of the outgoing flow. So if you want to write an mathematical equation for that one, we can write like this: V into dC by dt net. That means net change of concentration of A or net change of mass of A within the reactor, total reactor. That is why we are taking V into dC by dt, which is equal to Q into C naught. This is the incoming flow, Q is the flow rate, C naught is the concentration. So Q into C naught is coming to the system, minus Q into C, this much is going out of the system, and minus V into dC by dt reaction. So this is the change in mass of the reactant in the reactor because of reaction. So here we are using negative sign because the reactant concentration is decreasing with respect to time. But if the concentration of the reactant is increasing with respect to time, we have to use a positive sign here. And we have already seen that in biological system, the reactions, we are assuming that it is first order, and in CSTR or completely stirred tank reactor, we have seen that as soon as the water or the liquid enters in the system, continuous stirring will be there, so the concentration will be reducing instantaneously from C0 to CE. So the reaction will be becoming like this: V into dC by dt net. That means net change in concentration equal to Q into C0 minus Q into CE minus V into K into CE, because the concentration in the reactor is only CE. So this is very, very important. And we know that at steady state, the net change in mass of A in the system is 0. That means whatever is coming in and whatever is going out, and the reaction whatever is taking place, okay, the net, if you take, the net change in mass is 0. That is the steady state condition. So the equation will be becoming like this: 0 is equal to Q into C naught minus Q into CE minus V into K into CE. So we can find out what is CE by C naught, 1 by 1 plus K into T. That T is nothing but V by Q. So this is the T, T CSTR is equal to V by Q, or T we can find out T is equal to 1 by K into C naught by CE minus 1. So earlier we have seen what is the C for a CMBR reactor. That is T is equal to 1 by K into ln C by CD. D is the desired concentration, and when it comes to a CSTR reactor, T is equal to 1 by K into C naught by CD or CE, effluent concentration minus 1. And if this is the time required for a particular CSTR, we can put n number of CSTRs in series to get a particular efficiency. So if you want to find out the time required in a series of CSTRs, we can easily find out using this formula: C2 by C0 is equal to C1 by C0 into C2 by C1. This is happening in the first reactor, this is happening in the second reactor. So if you want to have Cn by C0, it is like this: 1 by 1 plus Kt CSTR raised to n, or n into TCF STR. That means total time. T is, this T represents the time required in one reactor. So if you want to find out what is the total time required in n reactors, n into TCF STR is equal to n by K into C0 by Cn raised to 1 by n minus 1, or in 1 unit, this is the time required, 1 by k into C naught by Cn raised to 1 by n minus 1. Why we are going for series of reactors? If you go for series of reactors, we will be getting more efficiency than providing a single CSTR with large volume. The reason is, if you are gradually decreasing the concentration, here if you provide serially, then what will happen? First it is changing from C0 to C1, then C1 to C2, C2 to C3 like that. So the concentration gradient available will be higher compared to a single reactor. Single reactor, what happens? It is changing from C0 to CE instantaneously. Here it takes some time to change to CE. So you will be getting a high concentration gradient. So it is always advisable to have a series of CSTR than having a single CSTR with large volume. That is an important point. This is important when we talk about oxidation pond design or pond system design in series. Now we will see the last type of reactor, that is the plug flow reactor. So plug flow reactor is something like this, okay, long narrow reactor. So there is no mixing, longitudinal mixing of the fluid elements. So if you take along the distance of the reactor, the concentration is varying, or we can say like this, the plug flow reactor, whatever the concentration change along the distance is similar to the concentration change in a CMBR, that means completely mixed batch reactor with respect to time, or any small volume of this reactor can be considered as a CMBR reactor, or in other ways plug flow is equivalent to a series of CMBR reactors. So now we will see. So here the distance as well as time is important to find out the concentration of the reactants or concentration of the pollutant. So the properties of a plug flow reactor are no longitudinal mixing between adjacent fluid elements. Each fluid element is analogous to a CMBR and position variable in a plug flow reactor corresponding to time variable in a CMBR. So how to find out the time required in a CMBR or in a plug flow reactor, that is change in the concentration of A due to the reaction of A in dt is equal to change in the concentration of A due to the position change of fluid element in dt, because we have seen that the time variable in CMBR reactor is equivalent to the position change in plug flow reactor. That is why we are writing like this. So we can write the equation like this, minus dc by kc with respect to time, how the concentration is changing, minus dc by kc, that is equal to how the position is changing. Dx is the distance and v is the velocity. So how the position is changing with respect to time. So we can integrate this one, then we will be getting like this, 1 by k into ln C naught by Ce is equal to L by V. So that is nothing but L by V, okay, V is the velocity here and L is the, because we are integrating it over 0 to L. So this dx will become L and V will be a constant. So this time will be becoming 1 by k into ln C naught by Ce. So we will be getting 1 by k into ln C naught by Ce is equal to length divided by velocity. So we can multiply both the terms by H into W, that means the cross sectional area of the reactor. So you will be getting L into cross sectional area is nothing but volume of the reactor and velocity into cross sectional area is nothing but Q. So V by Q is nothing but the time. So time in plug flow reactor is equal to 1 by k into ln C naught by Ce. This is nothing but the time required in a CMBR reactor. So plug flow reactor is nothing but CMBR reactors in series. So if we talk about the concentration gradient in a plug flow reactor, we will be getting maximum concentration gradient because there is no longitudinal mixing. So in the inlet you will be having C0 concentration and the outlet you will be having Ce concentration, and the concentration will be gradually changing. See, here we can see the concentration is gradually changing with respect to time. So the concentration gradient available will be maximum here in a plug flow reactor. So definitely the reaction rate will be more. So the volume required to achieve a particular degree of treatment will be less in plug flow reactor compared to CSTR reactor. CSTR reactor will require maximum volume and plug flow reactor will require least volume. Then why we are not going for plug flow reactors all the time? Because there are many advantages with CSTR reactors. Now we will see what all are the things we discussed today. So we have seen that the treatment option, either we have to go for physicochemical treatment or biological process, it is all depending upon the nature of the pollutant present in the system. But when we talk about the wastewater treatment, most of the time the solids present in the system is organic in nature. So the best treatment option is biological, because microorganisms can utilize that organic matter and convert them into carbon dioxide and water and more cells. So that is why most of the time biological treatment process is attached with wastewater. And now in wastewater treatment, okay, we will be having 3 different types of treatment. One is primary treatment, second one is secondary and tertiary. Primary treatment is all unit operations to remove settleable and floating solids, and secondary treatment is biological system, and tertiary depending upon the nature of the pollutant and effluent quality required. Then we have talked about what are the different types of reactions depending upon the rate. We have seen 0 order, first order, second order or nth order. But when we talk about biological systems, usually we assume that it is first order, and sometimes we assume it is 0 order reactor. And we also discussed about what are the different types of reactors. We have seen what is a CMBR reactor, what is a CSTR reactor, and what is a plug flow reactor. So if you want to achieve the same degree of treatment, CSTR reactors require maximum volume compared to plug flow reactor, because the concentration gradient available in CSTR reactor is less compared to plug flow reactor. But when we talk about wastewater treatment, because of many other advantages of CSTR, we go for CSTR in most of the times.